So Chen Ming Zhang is from the University of Queensland, is up next, and Chen Ming's also talking one of our knowledge priority projects, and he's speaking about the water and salt balance during recharge and drying in an environmental watering site in the Lower Murray River. Thank you.
Thank you very much, Rob. Hi everyone. So I'm going to talk about basically the water transport and salt transport at the Lower River Murray floodplain during environmental watering. That was the initial plan, and then later on we faced the floods, and then this project basically moves to look at the impact of floods to the water and salt balance. As said, a question in the morning, this outcome is slightly different from what Phil presented in the morning. So here is the site. So if you look at the site, it looks like a JellyBean shape. So this is a name from Juliet. And so Don was mentioning we need to give a sexy name to the project. And we basically call this one as the JellyBean project. Now, I'm going to talk about basically 5 parts: background, initial condition, and what really happens during the 2 big events, because the project has been running for 3 years. And then we'll talk about the outcomes from the environmental watering aspect, and then a comparison to the flooding impact, and then draw the conclusions. So the background, I'm basically show here a cross-section area of the River Murray. So on the right-hand side, we've got the river, but left-hand side is highland. Different types of formations are there. So lochs and sand and monument sands are usually interconnected, and the Coolumbijo clay sits on top, which is the alluvial depositions. The groundwater, so the irrigation there is on the highlands, which could potentially cause irrigation recharge. The groundwater level is intrinsically saline and is slightly higher than the river water level, and that allows the groundwater to move gradually to the river, which causes salt discharge. In the meantime, in this particular location, the environmental watering was carried out by pumping fresh water down to the low-lying area of the Coolumbijo clay. So what will that happen? So a pond will form, which we call environmental watering basin, and this area would have evapotranspiration, which takes water out with salt remain, but in the meantime, recharge may take place. The recharge and infiltration could slightly rise the water level, and this might be able to enhance the salt discharge. So at some stage, you improve the ecological conditions on the floodplain, but may have a little bit salt going down to the water table. So that's overall the conditions. So to be able to get the water and salt balance there, we managed to find out a site across the Lower River Murray. So this is where the site is located. So it's in a JellyBean shape, as we discussed. Here is the part of the River Creek. The other side is the orchard. That's where the highland is. And the diameter of the basin is about 240 meters. So walking across it will take almost an hour. So I just give a size of SUV, so that gives you a reference of how big this site is. As said, water is pumped in through a diesel pump. We in total pumped 100 megaliters of water to this particular site. The deepest water depth is about 1 meter. So rainfall and evapotranspiration is monitored by a weather station. So this is a relatively conventional method as compared to what is normal methods. And we know the surface area by DEM, so we can work out the infiltration and ET. Infiltration is also being monitored by the moisture sensors deployed underneath, so that gives the balance. So at the center, we have a ball deployed. The ball is basically measuring the rise of the groundwater table as a result of this ponding. And we also have 2 surface water level transducers that tells you the amount of water within the surface. We also did another similar deployment next at the perimeter. The reason we decided to do so is because the vegetation coverage difference. So here is more covered by the trees, whereas in the center, it's basically like the lower shrubs. So if there is any rise of the groundwater level, we are supposed to, it is supposed to dissipate it in all directions of this basin. To be able to capture that response, we deployed another 2 boreholes. So these 2 boreholes is able to find out whether there is any dissipation of the elevated groundwater as a result of this environmental watering. Now, this is a picture that shows so the processes during the natural flooding. So that's the difference So once the floods come in, then it inundates the entire floodplain, and as a result, it could cause recharge. But the recharge is a function of how conductive the soil is. So if it's very close to the riverbank, you might have a relatively large the recharge. But as the thickness of the columbidial clay increases, you might have a very, very small amount of recharge. But nevertheless, once the recharge is taking place, saturate the whole clay, what will happen is that the groundwater level will be the same as the river water level. If there is no head difference, there will be no recharge further taking place. Now, the moment when the discharge or salt load is increased is when the river water level goes back to the channel. And then we've got a groundwater level that is slightly higher than the river water level. And this is the location, time window when the salt load increases. So that was very similar to what Juliet mentioned in her presentation this early afternoon. So now, this is basically the situation at the floods, so we wouldn't be able to see where the JellyBean basins are. But what we managed to do is we basically bring, an inflatable boat to extend the stickouts of those boreholes, because we don't want water to go back in, so that it can, separate the surface water monitoring and the groundwater monitoring. So it's just the piezometer measurement during the floods, so give a bit difference. Now we need to talk about initial condition and timeline so that we are all in the same page. So once we went to the site back in 2021, that was a very, very dry year. When we went to the site, so you see the center of the basin is covered by shrubs, but the perimeter is these big trees. When we walk around, you can always see those barrels. If you shovel it, you see these channels are interconnected. This is basically sort of fertile soils. Once it's getting dry, the clay once getting dry, it starts cracking. And then later on, the wind brings a bit more clay and covers the majority of those channels, but you still can see some of the holes. We did the lab experiment, basically see the cracking processes. So that's the initial condition. Another very, very important initial condition we find is when we drill on the site. So we drill all the way through the columbidial clay, which is 6 meters. But once the drill bit hits the interface between the columbidial and the monument sand, we actually see the water level bounced up by 3 meters, right? What does that mean? It actually tells this aquifer is confined at this site, right? And this is not only taking place in one individual bore, but actually taking place for all of those boreholes, right? Now, if we put all those information all together, let's give an estimation. Is recharge going to take place as a result of environmental watering? Number one is we've got 6 meter deep of columbidial clay with the desiccation cracks and some of the trees. The number two is there is an aquitard, be able to bear the groundwater, saline groundwater, moving upwards to the clay by 3 meters. And the number three is that the confined saline aquifer. So if we put this message all together, is recharge going to take place? My initial guess is no. There are two possibilities. Number one is the clay is so impermeable so that the environmental water is just sitting on the top and allow it to evaporate and nothing will happen. So this is possibility one. The possibility two is that I'm aware of those cracks and also the tree. The tree may help the water to spread it within the columbidial clay, but they not be able to go through this aquitard. So that's the possible two things. And we actually send this power to many people, and then they all say that there will be no recharge to take place. You probably have your guess. Just bear that in mind. I'll show you the results. So there's the timeline of the project. So basically, the gears are all deployed in early 2021. And this graph here shows the time from 21 to almost like today. And then the y-axis is the surface water depth. So once it rises, that means we operate the pump. And then once it's going down, that is because of the evapotranspiration and infiltration. So we did another top up and then allow it completely dry. So this is where the basin completely gets dry. And then we did another environmental watering and allow it to dry, and then watering again and drop down. This empty window is the time when the flood comes in, so we have to retrieve the system. But once we get the access to the site, we redeploy our pressure transducer to see how it's depleting over time. So currently, the basin is completely dry, but there's a lot of moisture within the clay. So that's the timeline of this project. The key question, bear in mind, about this project is first, where does the environmental go? How much is infiltration? How much is the ET? The other second question is that what is the difference between environmental watering and natural flooding? The number three is, how do environmental watering and natural flooding influence salts? That's the key questions that we're trying to address. Now, field observation and the environmental watering. So this is the video taken at the early 2021 when the environmental water is introduced to a bone-dry columbidial clay. So you can see that the water is basically following all the cracks and then spreading around like a living serpent. This is Jess, actually. And it's quite exciting to see this dry environment gets revived as a result of this watering. If you look at the result, this is basically the monitoring result before the flooding. So this is time access from early 2021 to the end of 2022. That was when the flooding. I'll first introduce the videos. This top one shows where the flooded areas are. So we basically use DEM and water depths to reproduce this size of the basin. We also took photos at 2 different locations. So this is dropping down. But at some stage when it's getting dried, for example, this is surface water level. So it's completely getting dry. You actually can see some of the vegetation start shooting out because there's a lot of fresh water within the clay. Now, look at the graphs. So again, we mentioned these 2 watering events. So first the watering, and then dry pond, and then second watering. So we are aware of these 2 events taking place. This is the evapotranspiration measured by the traditional weather station. So we can see high evapotranspiration during summer, but very, very low rate during the winter. The cumulative rainfall during the 2-year period is only 450. We deployed moisture sensor in the control surface where it's never been inundated. The infiltration could only go up to half a meter. So rainfall-induced recharge is not possible at this site. Okay? Now, most important thing here, so this is the groundwater head, direct evidence. So the purple line here shows the surface water level. This green line is the groundwater level at SA3. So you can see that just immediately after the surface water pond is formed, the groundwater level at this site is increased by 2 meters just within 2 weeks' time. So we've got 6 meters of dry columbidial clay plus the aquitar, but they all been defeated by the environmental water. Now, if you look at the SA2, which is at the center of the pond, which is shown by the yellow color, so you see the rise of the water table is slightly later, but still managed to increase by 1 meter. So this is basically like a month's time window. They all increased, right? Then the other important evidence here is that the SA1 and 4, these 2 locations, has never been inundated, but they still be able to allow the groundwater level rise by 200 millimeters. So that's basically because the groundwater level increased here, but it dissipates in all directions. Now, there is a possibility, this actually was raised in the previous presentation. This is not caused by recharge at all. It's actually caused by hydrostatic loading. So it's like you've got a confined aquifer like a sponge, you put a heavy load, like a heavy dead weight, and that will also rise the groundwater level and then allow it to dissipate. So it's a geotechnical problem. Well, we don't believe, it's partially contribute to this, but it's not 100%. Because if we look at the salinity, you can see that particularly at these 2 locations, the EC dropped down from 50,000 to roughly a few hundreds. So these type of freshening could only be taking place by the mixing of the saline water with the fresh surface water and then dissipated in all directions. and it's fluctuating in between the two. So you can see it's kind of mixing and then dissipating. Temperature is also another signal that tells that the two waters is being mixed as a result of environmental watering. So that's basically the whole message we are delivering within this video. Now move to the next one. So what is possible, the conceptual model? So how the clay is able to be defeated by the environmental water. So we've got the ball lock, so it's pretty much dry until we meet with the aquitard. The aquitard seems to be quite less of oxygen, so it gives a silverish color. And we've also got these preferential pathways by the cracks. So the way how we conceptualize the process is that we've got 6-meter Coulomb-Bidgeot clay, but it can be characterized by the preferential pathway by the cracks formed due to desiccation, and also the roots. And the bulk clay, that is the big box of clay, which has a big storage. And the aquitard is able to bear the confined aquifer. But nevertheless, if you pump the water on top, it will immediately going down to the preferential pathway and then allow this aquitard to be saturated. Once it's unsaturated, it has a low hydraulic conductivity. But once it's saturated, it's got a relatively high hydraulic conductivity, which allows water to get in. And then a little bit infiltration through the bulk clay, but nevertheless, the water is moving laterally to those bulk clay. So one of the ways you could think about the Coulomb-Bidgeot clay is basically a big rock with a crack in between. So once you submerge that into the water just goes through the crack, but the bulk rock is not able to give a much infiltration. But this also rings, there is another question, how much clay could potentially be wet as a result of environmental watering? Because if it's crack of rock, the rock is still like dry, but Coulomb-Bidgeot clay, is that gonna be dry or wet? So we will later on find this one out. So as a water balance, I'll just quickly go through this table. So total water pumping is 60 megaliters, and that is 94%. The rainfall is only 4 megaliter, that is 6%. So at the end of the environmental watering, when it's getting dried, pond is 0 at the beginning, but later on it becomes 0 because it's completely dried out. ET took out 22 megaliters. Infiltration takes out 42 megaliters. So the ratio between these two is 1 to 2. Once we did the second environmental watering, similar condition, except that the ratio between ET and the infiltration is 1 to 1. And this difference is caused by the Coulomb-Bidgeot clay already being water saturated. So it doesn't need that much water to infiltrate. So vegetation response to the environmental watering is absolutely very evident. So you can see initially it's very, very dry land, but later on the water edge started to get relatively wet, greenish. And then if the pond is there for a year, you see aquatic vegetation start dominating in this area. So this is a picture taken after the floods. So you can still see some of the greenish vegetation shoots out. This is the picture taken just last month. So the basin is just dried, but underneath it's still very, very wet. Now, what happens during the 2022 and 2023 floods? I'm going to show exactly the same slides as what Phil shows, the groundwater level change over time. So here is July 2022. This is October 2023. And the y-axis for the very first graph is the elevation, so it's meter AHD. So how to look at these scribbles? So first of all, this site, this JellyBean, is about 3 kilometers downstream to Lock 6 and 11 kilometers upstream to Lock 5. So Lock 6 and Lock 5 is the surface water level. So that black line is the surface water level, and the cyan line is the surface water level at Lock 5. So if you try to interpolate the surface water level at this location, given it's very close to Lock 6, so I would say it's very, very close to the black line. Now, if we look at the groundwater level at these 5 piezometers deployed at a different location in the floodplain, you can see initially they are spreading, but later on, once the floods start covering the floodplain, as indicated by the vertical line, it started off converge. But the slightly difference is that you didn't really see an immediate shoot up of the groundwater and then later on drop down very quickly, which is caused by backflow, because we basically extend those stickouts to ensure they are survived. There is no backflow to take place. But you can see the groundwater level climbed up very, very quickly with the surface water level. So what does that mean? It means that for every single part of the floodplain, it start off infiltrating down, be able to saturate the clay and then allow groundwater to rise up. The other possibility is that the river water level managed to go through the columbidial clay and then uplifting from the bottom. But this process is much slower as compared to directly going down. So the only possibility is caused by infiltration. Then if you look at after the flooding period, so you can see the groundwater level is reducing gradually as well. So that's also an indication that once the surface water start off going down, there is a discharge taking place and then eventually allow the groundwater level drops down as well. And so during this window, which is a few months after the peak, the groundwater level within the floodplain is always higher than the surface water level. That's where the salt discharge is taking place. Now, if you look at this particular period, so log 5 is relatively low, but log 6 has got some operations there. So the surface water level shoots up again, and then it could cause a bit some inflow to the groundwater level to some extent. But at the end of this monitoring period, we can see the groundwater level is almost the same as the surface water level. The underneath two graph is the EC and the temperature, so that gives you another aspect of the mixing between the two. EC is fluctuating up and down, and then temperature, groundwater temperature is also quite fluctuating. That is also an indication of the recharge being taking place. In terms of the other two ball outside of the floodplain, so that's in the highland, we can see that it's basically increasing and become steady even 6 months after the flooding events. If this rise of the water level will return back to the normal condition, probably in the next 2 years' time. So we haven't seen it comes back yet. I'll just quickly show this chemistry data. So I use the chitin concentration to look at the groundwater boreholes, the chemistry. So yes, there is slightly decrease of the chitin concentrations, but not significantly. So what does it mean is, although the surface water somehow gets connected to the groundwater, but it's not a completely replacement. It's just a tiny bit of recharge that is able to freshening the top part of the groundwater. This is also a very important survey we did in October 2023 when the surface water gets completely dried. So we drilled 2 extra boreholes to see how much clay is wet, because one of the possibilities is that clay works like a rock. The rock body doesn't get wet at all. It's just the preferential pathway. So what we find is that the water level is 1.5 meters. And the water level within the clay is the same as the groundwater level. So basically, if there is a separate water level within the columbidial, it's the same as the groundwater. So that actually tells there is not much the impact of aquitard is almost not there. Instead, it's the moisture content within the clay is almost indication of full saturation, because it's relatively the same as the moisture content at 1.5 meters below the surface. But if you look at the EC, the only freshening area is just the top columbidial clay. But after below the water table, we can see that the EC is almost very, very stable. So why at this particular site it's being always sits with fresh water, but the EC can only refreshing the top 1.5 meters. The reason is that once the groundwater level rises, it also brings salt to the area which were previously refreshened, so that it's only the area above the water table that could potentially be refreshed by the environmental watering. This may give some implication about how we can optimize the environmental watering activity, at least from the hydrological point of view. And the other thing we did also is the ERT, and then the ERT shows that within the basin, we got a very, very consistent 1.5 meters of freshening surface as indicated by the blue areas. Similar things as the survey, so within the basin, it's relatively fresh, but outside, given most of the time, it's just a flash flood and then going out, so the refreshening is not significant, but within the basin where it's relatively low, the refreshening top 1.5 is quite consistent. So finally, I'll just show a kind of hydrological cycle within the Coulombigeal clay. So go back to the initial condition, the clay is dried with the aquitard. Although the water pressure is still higher than the aquitard, it's a confined condition. And then environmental water allows this fresh water sits on top within the Coulombigeal clay and dissipated in all directions. Recharge could take place, but this recharge wets up the aquitard and change it from aquitard to an aquifer. So this is actually a semi-confined aquifer, right? Then once the time goes further, this surface water level drops down by evapotranspiration and then gravity drainage. There's a huge difference between the two. Evapotranspiration takes water out with salt left behind. So if you got another freshening, it probably will get mixed. And then gravity drainage will take the salt back into the aquifer. And finally, these two processes will dry out the Coulombigeal clay, and we go back to 2021. Thank you very much.